This lesson is an introduction to hydrocarbons, and hydrocarbons are molecules that have hydrogen and carbon, so they're all C's and H's. All right, and there are many, many hydrocarbons, and they can be represented many ways. So we'll talk about a few different ways they can be represented. First of all, you can draw out the structures showing all the bonds and all the atoms, such as I show here and over here, and this would be referred to as the complete structural form. Or in other words, they are Lewis structures for the molecules. All right, but oftentimes that is too cumbersome and really unnecessary, because there are some different types of other ways to show it. And one of them, or actually more than one, a class of them, is known as the condensed forms, or condensed structures. Okay, so here are some examples. And for the molecule I'm showing up here above, this is the condensed form. So what it shows is each carbon, it focuses on the carbons, and then it has the hydrogens attached to that carbon listed after it, to the right of it. So this carbon here has 3 hydrogens, so it's CH3. The next carbon has 2 hydrogens, so CH2, another CH2, CH2, and finally at the end, CH3. For this other molecule on the right, the first carbon on the left has 2, so it's CH2, and the one on the right has CH2. Now this doesn't explicitly show the double bond, but the fact that carbon always has to have 4 bonds would tell you that there must be a double bond between those carbons in order to have 4 bonds on each carbon. Further, you can condense it even more. For example, this molecule on the left, which had 3 CH2 groups in the middle, you can put parentheses around the CH2 and a subscript showing how many of that group there are. So that can be another way of condensing them. All right, but let's look at another way that's even simpler. What if we just show, focusing on the carbons again, we just show the carbon-carbon bonds? So returning back up to the first molecule, if you look just at carbon-carbon bonds, you have one here, one here, one here, one here. There are 4 of them in a row, and since these bonds are actually in tetrahedral form, you know that they actually are going to be bent. They're not actually all in one line. They actually get bent. So you show here 1, 2, 3, 4 lines to represent those carbons. Now, since every carbon has to have 4 bonds total, you can figure out how many hydrogens are on each of those carbons. The ones in the end will have to have 3 hydrogens. The ones in the middle will have to have 2 hydrogens on them, as we see in the structure above. Looking at the structure on the right, you'll see that the only bonds between 2 carbons is the carbon-carbon double bond. So the only thing we show in this form is a double bond. Okay, there's a carbon at each end, and then there are 2 hydrogens to make a total of 4 bonds on each carbon. Okay, so these types of drawings are known as line angle, or sometimes structures, or sometimes called skeletal structures. All right, so they show only carbon-carbon bonds, whether they are single, double, or triple. Okay, so let's practice some of these concepts and different ways of showing structures by first taking structures on the left, which you're going to make complete by adding the hydrogens, and then you're going to write a condensed form, either the somewhat condensed or the super condensed form, whichever is more appropriate, and then you're going to draw the line angle drawing. And let's do one at a time. So let's do the first one. and then stop and try the second one. So hopefully you have already drawn yours. If not, stop now. Okay, so each carbon needs 4 bonds. This one on the left has 1 already to a carbon, so we're going to make 3 more and put H's on. The one in the middle has 2, so it needs 2 more, which are going to be H's. The one on the end has 1, so it needs 3 more. Every carbon needs 4 bonds total. All right, so the condensed structure means that we start with the carbon, write how many H's are attached to it, so 3. And then the next carbon, and how many are attached to it, and the final carbon, and how many are attached to it. Incidentally, you will sometimes see the H's for the carbon on the left put on the outside. In other words, you might sometimes see H3C and then CH2, CH3. Sometimes that is done. All right, the line angle drawing. Remember, we want only carbon-carbon bonds. There's only 2. One here, one here. We're going to angle them to show that they are 2 different bonds. And the joint in the middle would be the carbon in the center. All right, then try the second molecule. Putting in hydrogens, the end one gets 3. The next one has 3 bonds, a double and a single, so it only gets 1 more, and you can put it on top or bottom, it doesn't matter. The next carbon has 3, so it needs 1 more, and the final carbon needs 3 more. All right, the condensed structure, CH3 on the end, CH is the next one, and another CH, and finally CH3. And remember, you could go backwards from condensed to complete by realizing that these carbons all need 4, and so if the H's and the C's don't provide them with single bonds, you need to make double bonds to other carbons. All right, so then let's do the line angle drawing. You have a single, then a double, then a single. I'm going to draw it angled like that. You could also draw it going down on the other end, and in fact we will talk about those forms soon. Okay, on the next page we're going to talk about very basic, simple naming for hydrocarbons. In a later lesson we will talk about more complex naming, but we'll start with simple. All right, so with hydrocarbons, if there's nothing but carbons and hydrogens, all single bonds, then that is known as an alkane. Okay, and the ending of the root name will have ane, A-N-E, or yeah, without the S. All right, so this one happens to be with 3 carbons, happens to be prop, and so the ending would be ane. And you've probably heard of propane gas. That's what the molecule looks like. All right, but if you have a double bond anywhere in the molecule, 1 or more double bonds, that is known as an alkene, and the ending will have ene, just like the word alkene. So this one would be prop, because it's 3 carbons, but the ending would be ene. And then if you have a carbon-carbon triple bond anywhere in the molecule, it gets named an alkyne, and the ending will be ine, Y-N-E, so this would be propyne. All right, so these root names, where did we get the prop from? That's what we'll talk about next. The root names is dependent on how many C's there are. So remember, we just did 3 carbons. So if there are 3 C's, then we use the root name prop, and then the ending again will be ane, ene, or ine, depending on other things. All right, but for 1 carbon, that's meth. 2 carbons are F. 3 is prop. 4 is bute. 5 is pent, like the pentagon. 6 is hex, like a hexagon. 7 is hept. 8 is oct. 9 is non, N-O-N, not non, but known. And 10 is dec, and dec like decade. All right, so those are the root names. So now, using those root names and the endings for single bonds, at least one double bond or at least one triple bond, try naming, well, we will name these, and then I'll have you try ones at the bottom. All right, so here we have 2 carbons. 2 carbons is eth. So with just single bond, it's ethane. With a double bond, ethene, alkene, and a triple bond is ethine. All right, now it's your turn to try. Count how many carbons and put the appropriate ending on these to make a simple name. The first one on the left has 4 carbons, so the root name is bute, and it's got a double bond, so it's butene. The one on the right has 6 carbons, that's hex, and since it's all single bonds, that's hexane. As you start to draw bigger and more complex hydrocarbons, you realize that there can be multiple different ways to write the same number of atoms in a molecule, and yet they're different molecules. So these are known as isomers, and I've already mentioned one example back here on the last page where we could draw this molecule as this way or this way, and those are actually known as isomers. Those are trans and cis isomers. Okay, but what are isomers? Isomers are molecules with the same formula, but they are different molecules. So in other words, molecules with the same formula do not have to be the same molecule. If they are isomers, they are different molecules. All right, so if we look at these 2 molecules on the top and count the carbons and hydrogens, you'll see this one's formula is C4H8, and this one is also C4H8. Okay, but this one has a double bond in the middle, and this one has a double bond on the end. So they're not the same molecule. Those are known as isomers of each other. All right, so they have the same formula and different molecule. Now look at this next one down here. And notice it has a double bond also on the end, but it's on a different end than this one. But if you think about these molecules rotating in space, you could take this one on the right and flip it over 180 degrees, and it would be this molecule on below. It would be the same molecule. So if a molecule can just rotate in space to another one, that's not a different molecule. That's just rotated. That's taking something and rotating it. If you take your right hand and rotate it around, it's still your right hand. It hasn't become your left hand. Okay, so same thing with this. So these are not isomers of each other. They are the same molecule rotated in space. All right, but if these 2, and let's call these molecules 1, 2, and 3, if 2 and 3 are not isomers, then 1 and 3 are, because 2 and 1 were isomers, therefore 3 and 1 would also be isomers, since 2 and 3 are the same molecule. Okay, so 1 and 3 are also isomers. All right, then look at these ones below. Let's look at some different isomers. And this time we're going to do something other than hydrocarbons. We're going to take a base of 3 carbons, and we're going to put a fluorine atom on. The rest of the molecule will be hydrogens. So it's like a hydrocarbon where you replaced one of the hydrogens with a fluorine atom. All right, so I can put that F on the right-hand side of the molecule. I can put that F on the middle one on the middle carbon. Okay, well, just like above where the double bond was in different places, putting an F in different places will create isomers. They will have the same formula, but this one has an F on the end carbon, this one has an F on the central carbon. We can't rotate one of these molecules to create the other, so they're not the same molecule. These are isomers of one another. All right, but then Let's look at this third one. Let's put an F over here. The rest will be H's. Now how does that compare to these other two? Once again, you have to remember that the way we draw them on paper is not how the molecules are in space. Each carbon has a tetrahedral arrangement around itself. So these different bonds are actually at 109.5 degrees apart. So if this carbon has three things on it 109.5 degrees apart, then this third one is the same as the first one. You just move, whether you put the F up here or down here, doesn't matter. They're all equal. They're all the equal bonds. They're all equal angles. Okay? So this is the same as the first. So they're not, so it's not an isomer of the first, although it would be an isomer of the second. All right, so try some of this yourself. So I have three pairs here, and each pair decide if they are isomers or not. All right, let's look at the first pair. Remember that the different bonds off of a carbon are all equal. They're all the same. So that makes this a little tricky. All right, and the second one, let's look at these. Okay, let's circle the chain of carbons. There's chain of 4, so that's just like the one above. Now this one, the carbons are not in a chain. They form kind of a cross or a T. Okay, you can't, by moving this carbon to another position that it's bonded to the carbons it's bonded to, you cannot create the other molecules. So these would have the same, they have the same number of carbons, same number of hydrogens, but they are not the same molecule. So yes, these are isomers. All right, and then finally, another example where we have Fs. Okay, so we have 2 carbons and an F on the top of one, and over here we have the F on the bottom of the other. But realize that they're both an F on the end of the molecule, and both sides are an end. There's only 2 carbons, so either side is an end. So where you put that F, you could put it in any of those positions where there's H's, and it would always be the same molecule. You can rotate this molecule to make this other molecule, so these are the same molecule. And it does take a little practice to see these things. Finally, we're going to talk about aromatic molecules. Okay, so aromatic molecules are a specific, unique class of hydrocarbons that are cyclic. Okay, so they're cyclic. They have cyclic atoms, and they have alternate double bonds. All right, and there's one aromatic molecule that is very common, and an aromatic part that is very common, which is benzene, and that is a 6-carbon version of an aromatic molecule. All right, so that's the most common. Common version is a 6-carbon. All right, so one way we can show it is the full structural form. So we have a cyclic version of 6 carbons. Every other bond between them is double. All right, so that is aromatic. You can contrast that with this cyclic molecule of 6 carbons, but there's no double bonds. That's not aromatic. It's cyclic, but it doesn't have alternating double bonds. Okay, and that's actually known as cyclohexane. It's hexane because it has 6 carbons, and it's cyclo because it's in a circle. Okay, so it's not aromatic. All right, and we have other ways of drawing them besides the full structural form. And in fact, the line angle drawing would look like this. Okay, you have 6 bonds between carbons, and every other one is double. But what we often do is draw it like this, because we could draw the double bonds for this one in the opposite positions. We could draw it like this, which is the opposite positions of the first one. And so we draw it like this to show that it's really a combination of those two. All right, so those are skeletal drawings or line angle drawings of benzene. All right, so remember, but the criteria is it has to be in a circle, or it's cyclical, and it has to have alternating double bonds. So look at the 5 molecules I've drawn below and realize some of these are combination line angle and condensed structures, which is frequently done with organic molecules, and figure out which ones would be aromatic. Okay, this first one is cyclic, but there's no double bonds, so no. The second one has alternating double bonds, but it's not cyclic. This one over here has a benzene ring. It's got cyclic carbons with alternating double bonds, so that would be aromatic. The one on the left, lower left, is cyclic, 4 carbons and alternating double bonds, so yes, that would be aromatic. It's not the most common, it's not benzene, but it's still aromatic. And finally, we have a 6-membered ring with no double bonds. That would not be aromatic. Be sure you practice all these concepts. There's been a lot of material presented in this video, and it's very important that you practice these before you can feel that you have mastered them.